why GCD of A and B is equal to the GCD of B, A mod B. A mod B is the remainder when A is divided by B. I assume you know what GCD is, but just to be on the same page, GCD of two integers A and B is the greatest integer that divides both A and B. Let's see an example. GCD of 32 and 24 is 8. 8 is the largest integer among the ones that divides 32 and 24. Here's another example. 18 is the GCD of 90 and 36. Let's see this formula in action. Let's find the GCD of 32 and 24. According to the formula, the GCD of 32 and 24 is equal to the GCD of 24 and the remainder of 32 divided by 24. So we have 24, GCD of 24 and 8. GCD of 24 and 8 in return is equal to the GCD of 8 and 0. The GCD of 8 and 0 is easy to calculate, and it's 8. This is a recursive procedure, and the GCD of 8, 0 is the base case. Here's the code. If we have the GCD of A and B, if B is 0, we return A, else we return the GCD of B, A mod B. Let's see a trick to remember this formula. Let's say we have A and B is smaller than A, and B goes into A 2 times. Let's just suppose that B goes into A 2 times, and we have a remainder. Let's say there is some value C that divides both A and B. So it divides B, and also divides A, it divides B, and also divides A, and divides B, and also divides A. Now say that C is actually the GCD of A and B. Let me actually represent A as K times B plus R. We'll see why. So C is the greatest common divisor of A and B. Since it divides both A and B, it must, from the picture, you can say it must also divide the remainder. We can prove this with a simple direct proof. Let's regroup the terms A, K times B on the left hand side. Now let's represent A as M times C and B as N times C, since A and B are multiples of C. Now let's plot the common factor C. We obtain C times M minus K minus times N, which is equal to R. Now let's replace the term M minus K times N with an integer D. We obtain C times D equals R. From this, we can see that the R is a multiple of C. This completes the proof.